So last week, what we did is I introduced this concept, this mathematical concept called stoichiometry. Stoichiometry is the mathematical process, right? It's the mathematical process of combining unit conversions with molar ratios, which are your coefficients of your balanced chemical equation, the molar coefficients or the molar ratios, okay, to calculate the amount of chemicals in a chemical reaction. Okay, that's basically what I introduced last Friday. And for the most part, actually, a lot of it is repeated. It's literally just teaching you how to combine two old concepts in a new way. But it's all old concepts. You know how to balance, okay? You also know how to do unit conversions from unit 1. Now, you might need a little bit of practice. And don't forget, I already gave you guys that practice, unit 5 practice packet last week. It's also been available online because you have a test in 2 days, okay? And I'm not moving the test, all right? Because we've already moved enough days that we're not going to finish the curriculum in time if we keep moving things. So you just have to study, okay? But that being said, that's where we left off. And I'm going to do, today is going to be a big practice day, full of walkthroughs and then a little treat activity at the end. But what we have here is the key with stoichiometry is you have two things that you're always going to use or should be using, okay? Depending on the question. There's kind of two relationships that we use. We use molar mass as one of the relationships. And that means we can convert between grams and moles or moles and grams, depending on how we write the relationship. And we calculate molar mass via the periodic table. This is the periodic table. We figure out the molar mass via the periodic table. The second thing that we are constantly using in terms of numbers is we're constantly using the molar ratios of our balanced reaction. That gets us from substance A to substance B, or from substance B to substance A, depending on how you want to look at it. It helps us go between substances. You can never, ever, ever switch substances. Talk about grams of A to grams of B in one step. That's impossible. You have to go through the mole. It goes grams of A to moles of A, to moles of B, then to grams of B. You can never, ever, ever, if you're switching substances, ignore this. You have to go through the mole. You can never go straight from grams of one to grams of another. It's not the same. Because grams is super dependent on the unique characteristics, the densities, the unique mass of each molecule. But the ratio revealed in your chemical reaction coefficients is consistent. It's constant between those two species. Okay. So that is a big, big thing. And the way that the problems are going to work as we work through them is I might, in this kind of 4-step, anyone do race car stuff? It's like checkpoint 1, checkpoint 2, checkpoint 3, right? Anyone do like arcade games where they race cars? Anything like that? Really? Okay. Wow, some of you guys need to get out there a little bit more. So I should be able to drop you off at any checkpoint. I should be able to ask you to go from this step to this step. Or maybe I ask you to go from this step to this step. Or maybe I ask you to go from this step to this step. But the idea is that out of the 4 possible, Drea, out of the 4 possible transformations that can occur mathematically, yeah, I should be able to drop you off at any step and you just go through the motions. If I drop you off at step B, you go from step B to D. If I drop you off at step A, maybe I have you go all the way down to the finish line. Or maybe it's more like a relay. I only have you go a part of it. And then the rest of the is carried later. Okay. But that's kind of the big idea behind stoichiometry and the expectations I'll have for you on the test. Okay. So then let's look at this do now practice. Okay. So if I'm going to walk you through this, highly recommend if you don't write everything down, you at least write clues of the process to remind you. Okay. So, like for this problem, I ask you, I have 1.5 mole of H2O. How many moles of O2 do I make? So I give you in the do now, in the warm up, I give you the balanced chemical reaction. So the reaction that you're examining is that decomposition of water into oxygen and 2 hydrogen. Okay. This is a decomposition reaction of water. And I say that I start with 1.5 moles of H2O. And I want to end with moles of O2. So what we're seeing here is we're changing. You should be either writing this down or making note of the process. Okay. I am trying to help you, my dear. Okay. Do you want to sit so you can see next to me? Okay. So, what we want to do is we want to go from here to here. So the question is, what's the in-between part? What transforms it for me? What's going to get me there? Well, what you'll notice is I'm staying in the unit of moles, but I'm changing substances. I'm changing between chemical species. So what step must I go through to connect the 2 chemical species? What do I need to use? The molar ratios. Okay. And I can only use the molar ratios, by the way, if I'm in moles already. So like hard to make a difference when you have opposite units, right? Like you want to get into moles. So then the only thing you're changing is the substances. You can't change moles and substance at the same time. Okay. It's like, yeah. Okay. So what we're going to say then is to go from here to here, you have to use your molar ratios to go from one substance to another. So what I would say then is that I'm going to multiply 1.5 moles of H2O, which is basically like saying over 1, times my molar ratio is, well, I know for every 1 oxygen gas molecule, I decompose 2 water molecules, 2 moles of water molecules. Okay, 1 mole of oxygen is made for every 2 moles of water decomposed. So then, and here, maybe I'll even write that to help you guys a little bit more. Okay, for every 1 mole of oxygen, I consumed or decomposed 2 moles of water. And that ties directly to my balanced chemical equation. That's the standardized relationship between these 2 chemical species. And so what happens is what I see is my moles of water cancel out and I'm left in exactly what I want. Moles of oxygen. And so what I get then is I multiply my math. So it says 1.5 times 1 parentheses divided by 1 times 2. So then what I get is 1.5 divided by 2. What is that? 0.75 moles of oxygen are produced according to the ratio revealed in the balanced chemical reaction if I start with the specific number of 1.5 moles of water. But that leads us to the next thing. Okay. In our journey, that took us from here to here, moles of A to moles of B, moles of one thing to moles of another. But like in real life, you don't walk around and tell people, hey, can I have a mole of this? You say, hey, man, if you're a scientist, you're like, hey, how many grams? Okay. How many pills can I make? What are my milligrams? What are my grams? What are my picograms? What are my nanograms? What are my decigrams? Right? You say grams. So then what you have to do is now I'm going to ask you to finish this out by going from this stage to this stage, moles of one substance to grams of the same substance. So now what I'm going to do is I'm going to take my 0.75, question part 2, how many grams of O2? I'm going to take my 0.75 that I found in the previous step, and I'm going to say, oops, moles. And I'm going to say, okay, how do I, now this is my new start. And what's my new end? I want to get to grams of O2. So the question is, how do I go from here to here? Well, what I say then is what's a value, a standard value that connects moles and grams of oxygen? Molar mass. Because molar mass is a unit that is grams per mole, which gives me basically a fraction. So I say that, well, O2 is 16 times 2, 16 according to the periodic table for one oxygen, two of them together, 32 grams per mole, or moles per 32 grams of O2. So then what I write is 0.75 moles of oxygen times, I want to cancel out moles because like saying over 1, times 32 grams of oxygen for every 1 mole of oxygen. And what that gets me is my moles of oxygen cancel because 1 on top, 1 on bottom. And I just get 0.75 times 32 parentheses divided by 1 times 1. And I get what's 0.75 of 32? 24. Okay. I get my answer is that 0.75 moles of oxygen made specifically from decomposing 1.5 moles of water is measured in lab as coming out as 24 grams of oxygen. And that's how I would go from these 3 checkpoints right here. I just did a journey between these 3. I dropped you off at moles of A, checkpoint 2, and I asked you to go all the way to the finish line, grams of the new substance. Okay, so that's stoichiometry. You're only going to be dancing between molar mass and molar ratios. The question is, are you setting it up so they cancel? And are you tracking everything? Because obviously, if you flip the numbers, that's going to create a very different answer. Yes.
So for molar mass, is it just what column it is times however many there are?
It's the period. It's the average atomic mass times how many there are. So what's super cool about the periodic table is that the average atomic mass for one atom or one particle is the same number as a mole of them, just with a different unit.
So like the S,
Sulfur.
Sulfur.
Mm-hmm.
That would be 32, and then if there's 2 of them, it would be 40.
Mm-hmm.
Whatever that is times 2.
Yep. So for one sulfur atom, it's 32 atomic mass units, AMU. I multiply by a mole of them. What's the number for a mole? You have to memorize it. What's the number for a mole? Excellent. For a mole of sulfur, it becomes 32 grams for 1 mole. It's super nice. It stays the same number. It just changes units because we scale it up. Okay, it's really nice. So that's what we're going to be doing today with your little s'mores lab. Yeah, so as far as how did I get to 0.75, what I did is I started with my unique amount. I told you I have 1.5 moles of water. That's specific to my situation. But then I say, I want to get to oxygen, pure oxygen. How do I connect those two? What's the standard relationship between those two? My balanced chemical reaction gives me a standard relationship between these 2 molecules. That's what I use. So this comes from my balanced chemical reaction. It reveals to me my molar ratios. For every 2 moles of water decomposed, I produce 1 mole of oxygen diatomic and 2 moles of hydrogen diatomic. Okay, so let's switch over to the s'mores lab. So I'm going to download the s'mores lab. If you haven't already, please download the s'mores lab. Yes, me too. Where is my s'mores lab? 2022. Okay. Oh, great. No. Import. Did I not import it? Come on. Open. All right. So do you all have this s'mores lab in front of you? If you need a physical packet, it's up here. Okay. Do you need a physical packet? No? Okay. Huh? You will get to eat at the end. So what we're going to do today is you're going to take this idea of using your balanced chemical reaction with a s'mores. How can I calculate how many s'mores I can make given a certain amount of grams of ingredients I have? It's the same idea, okay? So what we're going to do is you guys are going to break up into groups, and I'm going to actually number you off, okay? And you're going to work through this. Every table is going to get a set of ingredients. You are not going to eat these ingredients because these ones are used for the general groups. Lots of people have touched them. You don't want to eat these ingredients, okay? But what you're going to do is we're going to make a chemical reaction out of s'mores. How to build a s'more. What's the ratio of ingredients for a s'more? And so what we're going to do is everybody's going to get a graham cracker, and we're going to give the graham cracker element a symbol. We're going to give the graham cracker the symbol of S. We're going to give the marshmallow a symbol of MM. We're going to give the chocolate piece a symbol of OR. And we're going to give the entire compound a chemical formula of s'more. SMMOR. And what you guys are going to do is, given your plate of sample ingredients, you're going to measure out in grams how much each element is. One item of each element. One atom of each element. And then what you're going to do is you're going to determine, well, if I know what each element mass is, what is the total mass of my compound, my s'more? And what you'll notice is you have 3 chocolates in that, okay? And you have 2 graham crackers. So when you add up the total, keep that in mind, okay? And that will give you the molar mass of your s'more sandwich. The total mass of your s'more sandwich. So you're going to walk yourself through several steps, okay, where it's going to one by one ask you to consider things. And the trick is here. I want you guys to set up unit conversion style. So like for one of these questions, it asks you how many, let's question D, part D. Based on the masses in your table, if you had a bag of marshmallows with a mass of 455 grams, how many marshmallows are in the bag? What you're going to see is you're going to set up that I start with 454 grams of per bag. Okay. Okay. And what you're going to see then is you're going to multiply by how many marshmallows, okay, by the grams. How many grams were for per marshmallow? And that would give you some number. It will give you some number marshmallows per bag. What I want you to notice in me walking you through this example here is that I want you to set up unit conversions. I know you can do this in your head. I know you could just do this with a calculator, blah, 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 blah. What I'm trying to show you is how do you do this process every single day without even realizing it, so that you can put what you know on a daily basis and put it in the format of the scientific mathematics, so that when you translate it to a chemistry equation that's with weird substances, you already see, oh, it's pretty much the same as what I'm doing here. It doesn't really matter what I'm telling you I'm working with. It just matters that you know the setup. So notice, I don't want you to just write 454 times divided by the amount of grams per marshmallow. Like you can do that in your head. I want you to show me with your math that you understand the process. And that means you're working with unit conversions, which means you should be writing everything pretty much as a fraction of some sort. Okay. So you guys are going to walk through this in teams, and you're going to pretty much get the entire day to do this. And when you're done with the s'mores analogy, okay, you have a chemical reaction that I will check as your final step. You're going to hand in this work at the end of the day. but I'm going to grade you on this section because this section tells me if you understood the previous. Okay, if you can do the previous, you should be able to do this section. I'm only going to grade you on this section because I don't really know how you would do this. Like, I assume you can do the previous if you could also do this section. Okay, so this is what you're going to submit part 2 at the end of today. And your goal is to leave no one behind. At the same time, if you're someone that doesn't fully understand this, your goal is to ask questions and engage. Okay, engage as much as you can. All right. So what we're going to do is I'm going to number you off and you're going to go into teams. One person is going to grab 1 plate of ingredients to measure out with your mass scale. Don't forget to tar and don't forget to take the lid off because that's going to mess you up. And don't forget to make sure you're in grams because if you're in ounces, that's also going to mess you up. Okay. So make sure you're in the correct unit mode on your mass scale. All right, guys. So I'm going to number you off. And then at the end, we'll reconvene and then I'll distribute out ingredients for those of you that want s'mores. So let's go over the s'mores lab, which was really more just calculation lab. It was group work, peer work, okay, to get you guys to talk to one another, support one another. And what we have is, what was your guys's, someone just give me their total mass for s'mores. Like, not every group's going to be the same, but what was one group's? Aislinn, what was your group's? 33.77. To make my life easier as I walk through the practice, I'm going to say 34 for my sake. Okay. So it's 34 grams per s'more, per a s'more. Okay. So it would look like this ratio. If I had to set it up as a ratio, or for every 1 s'more, I get 34 grams. Okay. I'm trying to put this very simple exercise in terms of your mathematical expectations on the test. So that when I give you weird but numbers and weird but chemicals, weird but formulas, you don't forget, oh, it's really just what I did here. It's what I do all the time in my head. Okay. So then what you got was a balanced chemical equation. This shouldn't have been too hard. 2 graham crackers, 1 marshmallow, and 3 chocolate pieces gave me a s'more. Okay. So what does the equation tell you? Well, it tells me how to make a s'more. What are the coefficients? The amount of each ingredient, the ratio of the ingredients to the s'more I make. So the ratio was 2 to 1 to 3 to 1. 2, 1, 3, 1. Okay. Then what you guys got to do is you got a series of hypotheticals. I have a bag of marshmallows that's 454 grams. How many marshmallows are in that bag? So immediately what you guys would do in your head is, oh, 454 divided by whatever the mass of your marshmallow was. So what was the mass of one person's marshmallow? Aislinn, what was the mass of your group's marshmallow? Okay, I'm going to call it 6 for the sake of my brain. 6. Okay, so what you guys would have just done in your head was, oh, 454 divided by 6. But what I wanted you to do is break it down. What were you relating to one another? You were really saying in your head that, oh, for every 454 grams per bag, I know that I have 1 marshmallow that is 6 grams. So what I do in my head is I naturally do this unit conversion without even thinking about it. I'm asking you to think about it. Okay, so 454 divided by 6, good Lord, somebody have a calculator. 454 divided by 6 is what? 74? Sure, we'll roll with that. 74. So then what I get is I have 74 marshmallows per bag. Then I get asked, okay, what's the maximum amount of s'mores I can get from this? So it's 74 marshmallows. And I know that for every 1 s'more, I need 1 marshmallow. So I say to myself, oh, I make 74 s'mores. This is what I'm asking you to do. Then I say, okay, well, then how many graham crackers do you need to make those 74 s'mores? Well, 74 s'mores. And I know that for every 1 s'more, I need 2 graham crackers. So I get then that can make 148 s'mores. Or sorry, I need 148 graham crackers. Gee willikers. I need 148 graham crackers, and that S looks crazy. Okay, space, graham crackers. Okay, so it doesn't look like it's part of the number. Okay, how many chocolate pieces do I need to make those 74 s'mores? Okay, well, 74 s'mores. And I know that for every one s'more, I need 3 chocolate pieces. So then it becomes 222 222 chocolate pieces to make my 74 s'mores. Okay. And if I'm a chocolate bar with a mass of 49, how many bars do I need to buy to make my 74 s'mores? Well, we could start many ways. I would start probably from, honestly, the 49. I would do 49.5 grams of chocolate per bar. I know that for every 1 chocolate piece, I have 6. What was my math for chocolate, Aislinn? Well, I'm just going with Aislinn's group because it's, oh, wait, you were in Aislinn's group. 3.7. Okay, 4 grams. That's not the right ratio. I'm going to flip this down to here. Okay, so for every 1 chocolate, I have 4 grams of chocolate. Okay, that cancels out my grams of chocolate, and I'm left with how many chocolate pieces are in that bar. Okay, so then I say, okay, well, I know that for every 1 s'more, I need 3 pieces of chocolate. Okay, and then I say, and I'm going to make 74 s'mores, right? That would be like your math. So we did all that. Now we're translating it down to actual chemistry. So here I have the reaction solid copper reacts with silver nitrate, AgNO3 aqueous, to produce a single replacement reaction, copper nitrate. And I was very nice. I just gave it to you. And silver solid. Okay. And I even tell you it's aqueous. And all you had to check was, what is this balance? It happens to be balanced. It's a 1 to 1 to 1 to 1. That's super nice. So then I say, okay, I start with 15 grams of copper and I want to get to moles of copper. Okay. I start with 15 grams and I want to end with moles of copper. So I'm going to use, to go from grams to moles of the same thing, I'm going to use molar mass. So I'm going to say times, what's my molar mass of copper? Yep. So I'm going to say for every 1 mole of copper, I have 63.5 grams. That's going to, of copper. That's going to get me grams of copper cancel, and I'm left with moles of copper. So it's going to get me a value of 15 divided by 63.5. What was, 0.24 moles of copper. Okay, now that I'm in moles, I ask you to determine the moles of silver made from this specific amount of copper I have. So I say, well, if I start with 0.24 moles of copper, I know from my balanced chemical equation that for every 1 copper, I make 1 silver in moles. So I say, okay, balanced chemical equation, molar coefficients, switching substances. Okay, I have 1 mole of silver for every 1 mole of copper. I cancel out moles of copper and I'm left with moles of silver. So I get a value of 0.24 moles of silver. But I don't want to tell my manufacturer how many moles of silver I can make because he doesn't care. That's not how he wants it packaged. It's like giving someone a gift in a paper box, like a paper bag. It's like not exactly what you want it packaged and presented as. It's still there. The value hasn't changed. The gift is the same, right? but how you package it matters. So what we say is, okay, moles isn't how people understand what I'm making. Grams, though, is. So what would be the equivalent value in grams for this mole amount? So I say, okay, I have 0.24 moles of silver. I want to get to grams. So I say, well, I know that the molar mass of silver is what? 107.9 grams of silver for every 1 mole of silver. So then I get, what's my value, Min? So 24.9 grams of silver. So then what we say is, from 15 grams of solid copper, I get 25.9 grams of silver, according to the chemical reaction I'm doing, according to the ratio of how much I start with and how much I end with. According to using my molar mass and my molar ratios. And that is the type of question I will be asking you to do on your test, but I won't be breaking it down as much. Okay. So, any questions? No? Okay. Good job, guys. So tomorrow is going to be a practice day. You're going to go through a crap ton of these problems. You also have a practice test that you should start doing practice problems with tonight. All right, guys. So it's more time.